Okay, today we're going to look at a little bit more about probabilities and when we combine multiple events. Yesterday we looked at the addition rule. Today we're going to look at something we refer to as the multiplication rule. Now, before we get into understanding what the multiplication rule is, we need to understand a little bit about independence. We call two events independent if the fact that the first one happens does not affect the possibility of the second one occurring. Now, don't confuse this with mutually exclusive events. You can have mutually exclusive events, meaning that they don't happen at the same time, and they would be very dependent on one another. So when we talk about things being independent, they can happen at the same time. They might not, they might, it doesn't really matter. So whether something is independent is completely independent of whether it's mutually exclusive or not. So independence is very important to understand if we're looking at the probability of two events happening, like one event happening and then the other one occurring after that. So if the events are independent, we simply apply the multiplication rule. And the multiplication rule for independent events basically states that the probability of A and B occurring would be equal to the probability of A times the probability of B occurring. Now, yesterday we looked at the addition rule, and the addition rule was talking about situations where we were concerned about the probability of A or B occurring. So make sure you're aware of the difference there. The multiplication rule involves A and B occurring at the same time, whereas the addition rule was A or B. Hopefully I said that correct. I think I did. Let's look at an example here. We have an urn or a vase or a jug. It contains three balls that are red, 2 blue balls, and 5 white balls. A ball is selected out of the urn and its color is noted. And then we put that ball back in, and then we're going to pick a second ball out. And we want to find the probability of each occurring. The first thing we want to check the probability of is selecting 2 balls, meaning that I would draw a blue ball on the first draw, and then put it back in and draw another blue ball again. So I'm talking about the probability of blue and blue, and that would be the probability of blue times the probability of blue. Well, we see that a blue ball can happen 2 out of the 10 occurrences. So we have 2/10 times 2/10. And when we multiply with fractions, it's very simple. You just multiply across the top, 2 times 2, and then you multiply across the bottom, 10 times 10, and we get 100 on the bottom, 4 on top. 4 over 100 simplifies to be 1/25. So in this scenario, the probability of drawing a blue ball on the first, putting it back and drawing a blue ball on the second would be 1 out of 25, or 1/25. What would be the probability of selecting a blue and then a white ball? In other words, we pick a blue, we put it back in, and then we draw a white. So that would be the probability of blue and white occurring, which would be the probability of a blue times the probability of a white. So in looking at the probability of blue, again, it's 2/10. We're going to multiply that times the probability of a white. Well, there were 5 white balls out of the 10, so that would be 5/10. So 2/10 times 5/10, hopefully you see by now, would be 10 100ths, excuse me, which would be 1/10. Getting a little ahead of myself, I made a mistake, but 10 100ths would simplify down to be 1/10. Part C, we're selecting a red ball, and then we're going to select a blue ball. Now, keep in mind, and I didn't emphasize this enough maybe earlier, these events are going to be independent of one another. And the reason why is because when I pull the red ball out of the vase or the urn, I put it back in. So as I pull that red ball out, the probability of me doing that was 3/10. I put it back in, and there's still 10 balls in there, and there's still 2 of those 10 would be blue. So we're going to say that these events are independent, and if we really want to say we shake it up a little bit or we mix it up after we do that, we have no influence from the first draw as to what the second draw is going to be. So again, we're looking at the probability of selecting a red ball and then a blue ball. So that would be probability of red and blue would be equal to the probability of red times the probability of blue. So that would be 3/10, because we had 3 red balls out of the 10, and the probability of a blue, again, would be 2/10. So we would multiply those together and get 6/100 or 3/50. Now, you might be saying, well, it doesn't seem like it would be that rare to happen, but when you look at the probabilities, there are 100 different outcomes that you could have. So getting them in that specific order and that specific manner, it does narrow it down quite a bit to only 3 chances out of 50. Now, that's independent events, meaning that the first event occurring has no bearing on whether the second one occurs or not. Now we're going to look at dependent events. Well, when the outcome of the first event has an effect on the outcome of the second event, then the 2 events are dependent of one another. Whether you do your homework has an effect on the grade that you're going to get in class. So whether or not you make an A in a class is going to be dependent on the probability of you doing your homework. So we're going to look at some examples here and tell whether they're dependent or independent, just to kind of help you understand a little bit more. Flipping 2 coins. Flipping 2 separate coins. What I flip on the first coin, the question we're asking is, does that affect or have any bearing on what's going to be flipped on the second coin? And the answer is no. So these would be independent events. The first coin has no effect on what happens with the second coin. Now, drawing 2 kings from a deck of cards without putting the first back. Okay, so I'll tell you that I want you to draw 2 cards from a deck. What's the probability of them both being kings? Well, when we draw the first king out and don't put anything back into the deck, the probability of drawing a king has now changed. First off, there's only 51 cards in the deck as opposed to the 52 that were there to begin with. And secondly, I had 4 kings to start off with, and now there's only 3. So that does have an effect on the probability of the second one. So these would be dependent of one another. Parking in a handicap spot and getting a ticket. Just to kind of clarify what this is saying is, if the probability of me getting a ticket at any random time that I drive my car might be one thing, but if I park my car in a handicapped spot, that probability is now going to change. The probability of me getting a ticket is going to increase. So the events here are dependent of one another. The probability of me getting a ticket is going to change if I start all of a sudden parking in handicap spots all the time. Playing basketball and getting an A in chemistry. Now, this is kind of funny, but if you really, we would like to think in theory that these should have nothing to do with one another. So playing basketball and getting an A in chemistry are independent events. I once had a student joke and say that, if the basketball coach was the chemistry teacher, it might have an effect on the grade. But in reality, we would give the teacher a little credit there and say that these events are independent of one another. In other words, whether you play basketball has no effect on the probability of you getting an A. All right. When we have events that are not independent, what we have is something, things are going to change. So we have to consider what we call conditional probability of an event when we are dealing with dependent events. The conditional probability of event B in relation to A is the probability that B will occur after A has already occurred. We will denote this. You will see it written in your book, and you'll see it written on the board and everywhere else as P, or the probability of B slash A, and that's actually a vertical slash. I don't know what the name of that symbol is. Technically, I guess it's just a vertical line there, or a vertical bar. But when we see that symbol, what it's saying is, what is the probability of B given that A has occurred? So if we know that an event A has happened, does that, and that has an effect on the probability of B, that's what we're talking about at that point, the probability that B would occur given that A has already happened. So going back to a deck of cards here, what is the probability of drawing an ace on the second draw if we already drew an ace on the first draw? Well, in other words, we are drawing an ace out of a deck of cards, and we want to now know what is the probability that we are now going to draw an ace on the second card as well. So we want to draw a pair of aces, in other words. Keep in mind, if we drew an ace on the first draw now, there are fewer aces in the deck. There were originally 4, now we're down to 3, as well as having fewer total cards. There were 52 originally, now we only have 51. So the probability of us drawing an ace, given that we have already drawn an ace on the first card, is going to be equal to 3 out of 51. We have 3 aces out of 51. So the conditional probability of drawing an ace after drawing another ace to begin with is much different than just the probability of drawing an ace. Now, the multiplication rule for dependent events is very similar, but we have to consider that conditional probability when we do it. If the two events are dependent, we must use the following approach. Probability of A and B would be equal to the probability of A times the probability of B given that A has already occurred. So we can't just multiply straight probabilities. We have to consider the probability now that B has a different probability now that A has already occurred. So as an example, find the probability of drawing 2 aces in a row. Our probability of the first ace then would be given, and then we would multiply that times the probability of an ace given that the first ace was drawn, which we just looked at. So in this case, that would be 4 out of 52 for the probability of drawing the first ace. The second ace, as we said, if we already drew one out, would have a probability of 3 out of 51. So we would multiply those two together, and we're going to get 12 over 2652. Now, that, of course, simplifies to be 1 over 221. But again, multiplying fractions, 4 times 3 and 52 times 51, and then we simplify. And that is the multiplication rule. Now, a little bit more about conditional probability. Sometimes it might not be so easy to see what conditional probability should be. We're going to use this formula when we are sometimes working with it, and that would be that the probability of B given that A has occurred is always going to be equal to the probability of A and B occurring at the same time, given that divided by the probability of A. Now, that can be helpful if we already know the probability of the two events occurring. We don't always know that. Sometimes we do. Sometimes we don't know the probability of B given A. And really, this is just reworking of the same formula we've already had. Here's an example where we might want to look at this. The probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. And the probability that he cannot find a legal space and has to park in the no parking zone is 20%, or 0.20. So we want to know what happens on Monday. Sam arrives at work and he has to park in a no parking zone. Find the probability that he's going to get a ticket. So we want to find the probability that he's going to get a ticket given that he has parked in the parking zone. Now we know that he's already parked in the parking zone. That's a given fact. So what is now the probability once that has occurred that he's going to get a ticket? So that would be the probability of getting a ticket given that we parked in the no parking zone. So we would divide that by the probability of him doing both, which we've already identified in the first sentence as 0.06. The probability of him parking in the no parking zone would be probability of A that would be 0.20. So we would have 0.06 divided by 0.20, and that would give us the probability of him getting the ticket, given that we know he's already parked in the parking zone, and that would be 0.30. Just a different kind of example there. You might see one or two like that where we're working backwards, and you would just divide the probabilities rather than multiply. Okay, your homework is listed in the note packet. Hopefully you've been following along with us. This assignment's going to be checked later on for homework assignment, and hopefully you can get through that. If you're having some questions, we'll be glad to discuss this a little bit more in class. And other than that, I hope you have a great day.